The Grand Central Terminal in New York City has a specific area called the Whispering Wall. If you stand on a corner of this wall, facing the wall, you can whisper into the wall, and any person standing on the opposite corner of the hall will be able to hear you clearly. Now, this phenomenon is strange because the two corners are over 30 feet apart, and the hallway is filled with busy travelers making lots of noise. And if you were to simply turn around and try to talk to the same person looking at them directly, they won't be able to hear you. So what's really going on? How can a whisper that can't be heard facing each other is clearly audible when facing the wall? In order to understand this, we need to understand a phenomenon involving waves called superposition. Up till now, we've seen how waves behave and the properties they exhibit when originating from a single source. However, what happens when a point in space is occupied by not one but multiple waves? Superposition occurs when multiple waves of the same type occupy the same space. In such a case, the resulting oscillations are the vector sum of the displacement of each wave. So, for example, if the waves meet in phase, that means their troughs and peaks match, then the resulting oscillations would be the sum of the amplitudes of the both waves. They kind of like add up. However, if the waves meet out of phase, that is, the troughs of one wave meet the peak of the other wave, the resulting oscillation will be the difference of the amplitudes of the two waves, kind of like cancelling each other out in a way. You can think of this in terms of forces acting on a point or on one particle. What you get as a result of these superpositions is either an amplifying effect or a cancelling effect. We often refer to this amplifying effect as a constructive superposition. We similarly refer to this cancelling effect as destructive superposition. Now, as you can imagine, if the waves undergoing such superposition in such a manner are of the same type, like sound or light, then the resulting constructive and destructive superpositions will be seemingly random. The waves will amplify each other at some places, but cancel each other out at other places. And these amplifications and cancellations will be of varying degrees and at varying positions. However, what will happen if the two waves are not only the same type, but also of the same frequency and at the same phase difference from each other? Well, in that case, you get what we call interference. It's the principle generally used in noise cancelling headphones when a set of microphones pick up sound waves around you and use it to generate the same coherent waves from the headphones, completely cancelling them out, giving you the peace and quiet you need to listen to some music. This phenomenon of interference can also be visually observed in water using two identical dippers that are made to vibrate at the same frequency. As these dippers move up and down, generating coherent waves, you can observe these waves interfere with each other, raising the waves' heights in regions of constructive superposition and completely nullifying the waves in the areas of destructive superposition. The same observation can also be made using sound from two identical speakers. As you move across in front of these speakers, you will be able to tell the rise and the dip in the volume of the sound. Here too is just like in the water wave example. Regions of constructive interference create higher volume, while regions of destructive interference create lower volume. We can in fact determine exactly where such coherent waves will create regions of constructive and destructive interference if we know their wavelength. For any point that is a multiple of a wavelength away from the source of the waves, we will get constructive interference. For example, if two coherent waves of wavelength 1.5 meters are generated from X, and X is 3 meters from both sources, the point will experience constructive interference. This is because at 3 meters, the point is exactly two wavelengths from both sources. Therefore, for any path difference, that's a multiple of the wave, and you will always get constructive interference. Similarly, destructive interference happens when the trough of one wave meets the peak of another, or when the waves are at 90 degrees out of phase. This happens when the path difference between the wave is half a wavelength apart. So for any point that is half, or 1.5, or 2.5, or 3.5, and so on, wavelengths apart, you will get destructive interference. This can be represented by the formula n plus half lambda. So if the two waves have a wavelength of 3 meters, start out 4.5 meters apart, they will generate destructive interference, cancelling each other out. This phenomenon of interference is exactly what's happening at the Grand Central Terminal's whispering wall. When you turn towards the wall and whisper, the sound waves from your mouth are deflected from different points of the curved wall, traveling across the hall to meet at the other corner in a region of constructive interference. As a result, even though the waves have low amplitude, they all add up. The waves created by all the reflections, they all add up and allow the listener at the other end to hear every word clearly. This property of interference is something that's widely used in whispering galleries across the world. Allow people in galleries to communicate without disturbing the audience on the main floor. Now, interference isn't the only interesting phenomenon coming out of superposition of waves. As you learn in later videos, superposition gives rise to a lot of different exciting things, including stationary waves and light patterns. So it's very important that we understand these basic principles of superposition of waves to further advance our learning of how these phenomena manifest themselves in the real world. Now, before we leave, see if you can figure this riddle out. You try to take a call in the middle of a noisy open air concert. The concert is being played out of two speakers that are 20 meters apart. Assuming that the sound coming out of the speaker have an average frequency of 300 hertz. Where will you have to stand in relation to those two speakers in order to find the quietest spot? Now you can use 330 meters per second as the speed of sound in air. Let's see if you can try that out.